Welcome to our second plenary talk. I'm very happy to introduce my colleague and friend, René Vidal. René is the Herschel L. Snyder Professor of Biomedical Engineering. And if you go read his bio, he says he also has a joint appointment in electrical engineering and in computer science and mechanical engineering. All those are extreme. Oh, and if you read further, he says, oh, and I do, I apply computer vision techniques to counting blood cells by imaging and building medical devices and robotic surgery. So he might paint this picture of a medicine bio guy, but don't be fooled by it. You have to read the careful text. Somewhere it will say he's the director of the Mathematical Institute of Data Sciences. And then slowly his true colors start coming out. So he should really be called a mathematician. And in fact, when he first came here to Hopkins from, I think, Berkeley in 2004? Three. So he came here and he interviewed. And of course, the interview was through the Whitaker Biomedical Institute, and so his appointment was going to be in BME. And I was trying to persuade him to sort of be in electrical engineering instead. And his argument was something like, no, BME is the #1 ranked department. Hopefully I'll get better students there. But of course, he came to Hopkins, and guess where his first few students were from? Electrical engineering. So, and why? Oh, well, they know better math than the BME students, or something like that. But anyway, he lives happily in multiple departments. He does a lot of foundational work in the mathematics of, I would just say, learning algorithms. He's known for his computer vision work, particularly his work on video, and more generally in high-dimensional data analysis. I think his thesis was well cited for some generalizing PCA. There was a GPCA idea, which is quite nice, doing multiple subspaces. He's had a whole series of papers in general in taking time series in high-dimensional data and doing analysis with that. His group, he's of course the director of the Math Institute as well, which is a relatively new thing at Hopkins. But otherwise, his research group is called the Computer Dynamics and Vision Lab or something. No, Vision Dynamics. All I know is it reduces to Vidal. So that's the short form for his lab. So he's also, of course, a fellow of the IEEE. He has a number of paper awards and this and that. But what I told him to talk about today is something that he's been thinking about quite hard for several years, trying to prove why some of these deep learning algorithms do as well as they do. I think somebody called it the unreasonable effectiveness of neural networks. René is going to make it sound a little bit more reasonable today with some of the things he's been thinking about. Please welcome René Vidal.
Thank you, Sanjeev. Thank you for waking up early and coming today. So neural networks did not begin in 2012. They began in 1940. At that time, people were thinking just about a single neuron, and they were thinking about maybe closely related to logic units, that they would just produce yes or no answers or ones and zeros. And even in the 1960s, there was the first algorithm for training the weights of those simple networks that was called Adaline. And what is very interesting is that while at the time it was sort of the beginning of artificial intelligence and everybody thought that we were going to replicate human abilities with these neural networks and they were able to put them into robots that will reason as we do, they were somewhat quickly abandoned, and that led to what is known as the first neural winter. And interestingly, the reason why they were abandoned was that someone realized in 1970 that, and so they had a second life or a renaissance in the 80s and 90s, and that was due to a number of things. So one of them was perhaps that they started to continue to use real valued networks as opposed to just 0-1. They started to build bigger networks by connecting multiple perceptrons with maybe more than one layer. But also some of the training algorithm, backpropagation, was invented back in 1982. And I say invented, it's a little bit loose, because if you think about what backpropagation is really gradient descent, which is of course an older algorithm. And it's gradient descent combined with the chain rule. So probably this would be even several hundred years old algorithm. The other reason why they became very popular is for the first time they were used for a little bit bigger problems. So one of them was the ability to recognize digits, and the other one was the first algorithms for being able to do speech recognition. So in fact, LSTMs were invented back there in 1997. But speech recognition method based on neural networks were even earlier than that. Again, maybe they sort of disappeared, and they sort of disappeared for most of the 2000s. And I would argue again that, like in the 70s, the reason was theoretical. There was something at which they didn't work. And here was the fact that we couldn't understand them. And in addition, the alternative, namely how otherwise we can do classification, was based on SVMs. And SVMs, or linear classifiers, require solving some convex problem. So when we talk about convex problems, we can think about what is the global optimum. And we can now try to figure out how well is this classifier going to do in other examples. But we couldn't do that for neural networks. And so they were abandoned and effectively substituted by SVMs or extensions of SVMs, or in fact a great variety of statistical methods. In speech, for example, HMMs were sort of the way to go. And as you all know, there's been a revival, like the third life of neural networks, ever since 2012. And some of the reasons, the first reason is in computer vision, most of the 2000s, we were doing classification, and we were doing classification by taking images, extracting some features. Typically those features would be histograms that had to do with distributions of edges in the image, and feeding them to a classifier that would typically be an SVM or a variant of an SVM. And performance on most databases was increasing, 0.5%, 0.5%, and around the end of the 2000s, the performance was kind of plateaued. And all of a sudden, in 1 year, in one paper, there was this 10% improvement on ImageNet, which is a database with that has 1,000 object categories and 1.2 million training examples. So here is an example of the evolution of performance in ImageNet ever since. So blue is methods based not on deep learning, and red is method based on deep learning. And you can see that that was the performance back then. So 33% and 26%. And so that is the 10% improvement that I was talking about. And from then on, everything became red. So 11%, then 6%, then 3%. So in a matter of 4 years, performance went down from 30% to 3%. Okay, so that's one example. A similar impact has happened in speech. I think Sanjeev would speak infinitely better than I possibly can about this topic. But he would also tell you that things were done with statistical methods, and that today everything is done with deep learning. And he would also tell you that performance is just, or the errors have dropped out dramatically in the last 5 years or so. And I guess we can probably tell if you talk to Siri 5 or 10 years ago versus today, and Alexa didn't even exist 10 years ago. And the improvement is clearly dramatic. But the same is happening in playing games. The game of Go, for example, deep learning or deep reinforcement learning algorithms have beaten the world champion at Go. And it's been done for other games. And it's true for pretty much anything today in the area of pattern recognition. So if you're theoretically inclined, you can start thinking, well, why does this happen? Why things that we couldn't do for so long now can be done? Or why is it so much better than SVMs? Or why is it so much better that having a real expert figure out what the features are supposed to be and then apply a classifier? And so when you talk to the people that develop these systems, the first answer that's given is, well, we're learning the features. and learning the features for a particular task has to be better than handcrafting them, or using the best possible domain expertise as to what are the better features to be extracted from that data. Okay, so that's one potential answer. The other one is, why go deeper? Why have many, many layers as opposed to one layer? Like an SVM in a sense is kind of just a one layer thing. And so the answer that is given, and this is empirical, by the way, so the x-axis here is the number of layers. The y-axis is what is called mean average precision. This is on the ImageNet dataset. And you can clearly see that the more layers, the better it performs. And so why? So the reason that is given in the case of computer vision is that low-level layers of a neural network capture, the more layer you add, the more invariances you capture. In a sense, you want to do recognition despite geometric transformations, where the object is, rotations, translations, changes of illumination, and so on and so forth. And the more layer you add, the more invariances you capture. In particular, if you think about deformations, there was this very nice paper, and maybe this is the only one that actually proves it a little bit more theoretically, kind of suggesting that if you've got an arbitrary deformation of the image, then every layer kind of does the first and second and third and fourth order Taylor expansion of that transformation. Obviously, we can do things today because we have a lot more data. You have now networks with 60 million parameters. You couldn't do training on them with only maybe 100 images. So the fact that we have 1 million images that are fully annotated obviously helps. And the fact that we can train very large networks with, quickly with GPUs also has to help. But there's been a few other changes. So in fact, if you think about the networks from the 80s versus the networks today, it's fair to say that the changes are not dramatic. And here's one of the changes. How do we train them? So we train them with backpropagation. And backpropagation is gradient descent, or today is used stochastic gradient descent. But when it comes to regularization, namely how do you prevent these networks to overfeed the data, there is this technique called dropout, and there are many others and many variants and extensions of it, that is basically somewhat strange in the sense that you say, well, I'm going to set to 0 half of the neurons and only update the weights of the other half. And I will select at random this half at every iteration. So why that works, again, seems fairly mysterious. The other change that's happened is that in the 80s and 90s, this blue curve was kind of the preferred nonlinearity that it was used. So the nonlinearity is the activation function, and it's meant to replicate what a neuron does, that below some threshold, it doesn't respond, and above some threshold, it has full response. And they were replaced by this red curve that is called rectified linear unit, that is 0 below some threshold and the identity above some threshold. And when you ask people why this is a good idea, this is the answer that is typically given. They say, this function here has a gradient that is 0, and a gradient that is 0. And if this curve is very steep, the gradient is 0 almost everywhere. So they say if you're training with backpropagation, then you're going to get this vanishing gradient problem. Namely that you're going to easily get stuck because your gradient is too small. And so that's why your optimization is not going to work. And they say, well, this is much better because now the gradient is the identity. And so now you don't have the vanishing gradient problem. So I collaborate with a mathematician who does optimization. And let me say that I try to give that explanation to a person who does optimization. He would say, well, and so what? I mean, the fact that the gradient vanishes versus not does not guarantee that I will find the global minimum in any way. So I think it's fair to say that while these are all potential answers, and they all seem reasonable, plausible, and perhaps, they do not seem very rigorous in any way. And so I think it's fair to say that the theoretical understanding of deep networks remains very shallow. So let me introduce some notation just in move forward in order to motivate what are the theoretical challenges in deep networks and how we can potentially have an avenue to tackle it. So just as a matter of notation, I'll typically denote the inputs to the network with X. The W's are going to be the weights, and they get summed. And then there is this activation function that is either that sigmoid or either that rectified in a unit, and that produces the output. So that's going to be just one unit. So when you have multiple layers and multiple neurons, this is where we're gonna notation we're going to use. We begin with the input, which is now going to be a vector, potentially. Or, in fact, I'm thinking here even matrix. This is just all of the training examples, okay? And so the number of rows of this matrix here is the number of training examples. So every row is one input. So what we're going to do is that we're going to apply now a linear transformation to it, and that's going to be represented by this matrix of weights W1. Okay, is that clear? Yeah. And then we apply a nonlinearity, and that is what produces the values at each one of these nodes. So then what we do is that we repeat. We have a second layer of weights and a second nonlinearity, and then we repeat this k times to produce the output. And the output is now going to be again a matrix. That is the number of labels, for example, and the number times the number of training examples. Okay, so I'm going to use this function phi. That's going to appear a lot throughout the talk. That is really the output of the network as a function of the input x and the set of all weights from all layers. So that's that function phi. So what are the theoretical questions and where do they arise given this notation? So the theoretical questions arise from the following. I've got this machine. Let's say that I'm trying to recognize faces, just to give a concrete example. So the input is images, the output is, let's say, just two faces, whether it's a Jeeves face or my face. So Y would be the category, X is the image. So there is some ideal map that takes images to labels that I don't know, and that's what I'm trying to estimate, and that's what I've denoted here by phi star. Okay? So what we're going to do is that we are going to try to find a network parameterized by some weights that minimizes the expected loss. The loss is the loss between Y is the labels, phi is the prediction of the network, and I am going to minimize that in expectation with respect to all possible input images and with respect to all possible output labels. And that's what I like to do ideally. But when I do so, I already commit to an error. And the error I commit to is that I've decided that the relationship between the input and the output is a neural network with this map phi. And that map, that when I do this optimization over neural networks, that class of all possible neural networks may include or may not include that phi star, which is the truth. Okay. So the second problem is that in reality, I don't know the distributions of the inputs and the output data. So instead of minimizing this ideal quantity, which is the expected error over all x and y's, I'm going to do this minimization only over my training examples. So I'm going to replace that expectation by the sum from 1 to n of the losses only over the training examples. Okay? So that is minimizing the empirical loss on the training data versus minimizing the expected loss over the population of all set of images. Then there is the approximation error. That's what I already spoke. There is the error between what I would like to optimize ideally, that's what the expected value is, versus the unknown true map. And that's what we're going to call approximation throughout this one. Okay? That error comes because the true function that I'm trying to predict may not belong to the class of functions that I'm actually optimizing over, which is the class of neural networks. Then there is this generalization error that arises because I would have loved to optimize that statistical quantity over the population, but in reality I only have access to the training set, so I'm going to optimize this quantity. So the difference between the two which is here, is what we call generalization. And the last part is the following. Really, if this problem was convex, I could find the global optimum. But in reality, I'm going to run gradient descent, and I'll stop after some number of iterations. So I'll find some optimum, and that need not coincide. So this is so bottom line. This is the set of weights that I actually find. This is the set of weights that corresponds to the global optimum of the empirical loss. The difference is what I call the optimization error. Okay? I repeat, this is the set of weights I actually compute. This would have been the global optimum. That induces one error. Here, this is the global optimum of the empirical loss. This is the global optimum of the expected loss. They're not the same. And this is the global optimum of the expected loss. This is the value of the true phi that I'm trying to estimate. So there are three quantities that you should be worrying about.
So, René,
yes.
If you can make a comment. So that means that if I want to reduce the first error, I should think of a bigger model or a bigger class of models.
Good. Very good. Actually, let me emphasize that. So Sanjeev's totally right. How would I reduce or eliminate these errors? This is the error because the class of functions I optimize over may or may not cover the true function. So how do I make it smaller? As Sanjeev said, you make the network bigger. If the network can cover more and more and more functions, right, then you make this smaller. This one is now the generalization error that tells you, this is how well you generalize. So typically, if you increase and you make your network bigger, you will overfit. So you will not generalize well. So that's why the sum of these two kind of gives you the right trade-off. That this one tells you make your network bigger. This one is supposed to tell you make your network smaller.
Or get more data.
Or get more data. Okay? And this one is kind of different because usually when we're just doing linear SVMs, the problem is convex, so we're supposed to be able to find the global optimum. So we don't have this extra error.
So for the last one, did you say be smarter about the optimization?
So the last one could be smart about the optimization, but, and this is what I'm going to be talking a little bit, or let me just say here, because the networks are so big and so over-parameterized, and the number of examples we're training them is much smaller than we should, you end up maybe with many global optimum, and that's what I'm going to be arguing. And therefore, the optimizer might be preferring some minimum to other in practice. But different minima might generalize differently. Okay. And therefore, while in classical linear classification, I only have to worry about this, that is why now optimization plays such a big role on whether your machine generalizes well or not. That it shouldn't have, because all what optimization was supposed to do is to find your global optimum. But today, which minimum I pick seems to generalize differently. Okay, so that was also kind of explained a little bit in this slide, which is that the architecture is designed to control the approximation error, as I just said. The bigger the network, probably the smaller the error. What happened is that to prevent the overfitting, what we actually minimize is that loss that I was talking about, but we add a second term that is the regularization. And that second term is meant to prevent overfitting. Okay? And so now I can play with these three things. I can choose the architecture, I can choose the regularizer, and I can choose the optimizer. And the goal, in theory, should be to minimize the three errors, or the sum of the three. Okay. So I hope I've convinced you that from a theoretical perspective, there are three fundamental questions. The first one is how do you design the architecture? The second one is how you optimize. And the last one is what are the generalization properties of a machine? So regarding the first question, what you care about is, well, how many layers? What is the size of every layer? How do I choose them? What kind of nonlinearities do I put? And so on and so forth. these questions are by no means new. So if you look at the previous lives of neural networks, they already had come up with this idea that even neural networks with a single hidden layer are universal approximators. What does that mean? That effectively they can approximate any function arbitrarily well. Of course, there are some theorems and more precise conditions. So think, for example, that the function was a continuous function, just to be a little bit more concrete. And so the idea really is that as you add more and more neurons to that single hidden layer, eventually the error in approximation will be within any pre-specified epsilon that you give. That would immediately tell you, well, if networks with a single hidden layer can approximate any function, why deep networks work better than shallow networks? Right? And so that question has motivated much of the ongoing research in this area. And let me just highlight some names of some of the papers, like gaps between deep and shallow. Maybe. So what is it that's going on? The reality is that the results from the 90s told us that there were universal approximations, but they didn't tell us the complexity measures. Namely, if you give me an epsilon, you want to approximate any function within an epsilon, how many neurons do you need? And so if the number of neurons you need is overwhelmingly large, let's say exponential, maybe you should, sure, the result is true, but you really need very, 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 very wide networks to achieve that. And so it could be possible that it's much more economical to have networks that are not as wide, but with a few more layers, and you will be able to achieve the same epsilon with much fewer neurons, for example. And that's exactly what many of this recent work is worrying about, which is that, and there is this so-called, actually this is what this paper is about, there are exponential gaps between deep and shallow networks, that you can, the number of neurons that you need is exponentially smaller when you use deep networks than when you use shallow networks. So a first reason, perhaps, for using deep networks is that they have, I wouldn't say better approximation abilities, but maybe I would say that they can approximate within the same epsilon with much fewer neurons. The second question is optimization. So the challenge is that the problem is non-convex, and so you can be in this situation. Local minima, local maxima, flat valleys. You can have isolated global minimizers, or you can have a complete flat valley of global minimizers. So back in the 90s, there was also work, of course, in optimization. So already in '89, someone had shown that there's no spurious local minima for linear networks. What does that mean? Spurious local minima are local minima that are not global. So going back to this picture, that would be a spurious local minima. And so linear networks is if you have non-linearity, single hidden layer, sort of the simplest possible case. But other than that single good result, which is the very first one, most others were very negative. Namely, backpropagation fails as soon as you put a nonlinearity. It only converges when the data is linearly separable. Otherwise, it gets stuck. There are local minima and plateaus and lots of bad things for multi-layer networks. So that was the state by the year 2000. So again, today, this is an area of research that is very, very active. The first suggestion that the problem might be doable was, I think, 2005, where they say, let's take a network with a single hidden layer, and let me just increase the number of layers to infinity and put a sparsity prime. In that case, they were able to reformulate the training problem so that it would be convex, because then it's just the selection of how many neurons, really, and that can be done with an L1 penalty. There's been a lot of work on understanding the loss surface, and much of it is trying to make connections between optimization and statistical physics, the energy landscape of physical systems. Much of it, in my view, is based on a lot of approximations. that are not representative of the actual neural networks. So I'll speak in more depth about our recent work in that topic in a moment. So I will not say more. And the last question is this question of generalization. So how well networks generalize, how should they be regularized so that they generalize well, and how do you prevent overfitting? So the situation on the top is the situation you'd like to be. If the boundary between class 1, the red class and the blue class, is simple enough, small perturbations to the location of every point will not change its class. But if the boundary is very complex, like here, if you move the red point a little bit, it will become blue. Okay, so the ability to generalize really has to do a little bit with that. And so ideally, we would like simple boundaries as opposed to complex. If you look at the results from, again, I think this is 1998, they computed how many training examples were needed in order to achieve a small generalization error. And the number of examples grows polynomially with the network size. That was the calculation that was done. So polynomially with the network size, I don't know, let's say that it was quadratic. So if you had 100 neurons, then you need a number of examples, it's 100 squared. Now let's take AlexNet that has 60 million parameters. So the number of training examples would need to be, say, 60 million squared. How many training examples are there in AlexNet? 1 million. It's not 60 million squared. So these theorems are there, and everybody thought that, everybody in theory thought that all of the work in the neural network was nuts, because the number of examples really needed for these machines to work should have been so much bigger than what's actually being used. And so there is a big gap of understanding there, and maybe the answer is that we're not doing it right. And so there has been a lot of work, let me begin with the last one, about rethinking generalization, that maybe the number of neurons is not the right thing to count. Okay. And we need to have new measures of complexity to measure how big a network is so that we can do this comparison right. But regardless, the classical way of doing regularization is really penalizing your optimization with the sum of the square of the weights. But people are proposing a lot of alternatives. So I'd like to just highlight one, because it will happen a lot in this talk, is this product of weights. So the bottom line is that people are proposing different measures of complexity, as well as different functions of the weights that better characterize generalization. And which one is the right one and which one is the wrong one? I would say that we are still at a state where the bounds are very loose. Maybe not as loose as the bounds from the 90s, but still too loose to know exactly how to do this. And this is a very active area of research. The other thing that further complicates is that most people are no longer using classical ways of doing generalization. By classical ways, I mean explicitly adding an extra term to the optimization problem. So what's being done today is things such as dropout that really seem like a very random procedure. So why is it adequate remains a mystery. So I hope to have conveyed the idea that there are three key questions: architecture, optimization, and generalization. That they're intimately related. Optimization can impact generalization, architecture can impact generalization, and so on and so forth. And that figuring out that interrelationship is going to be the core at understanding why deep neural networks work so well. That being said, I do believe that a unifying theory will emerge, and I think we are beginning to see the tip of the iceberg with these three works that I'd like to highlight here. So the first one is this work showing that a well-known regularization technique, that is a dropout, actually is not doing something fully random or unexplainable, as we thought. It's actually adding an explicit form of regularization. and it is related to the product of the weight of the null. Okay, so that's the first one. The second one is this paper from Sapiro and colleagues showing that if you add products of weights as a regularizer, that tends to generalize well. And the last one, and that's primarily what I'm going to be talking about today, is that if you add the product of weights regularizer, then you can have guarantees of global optimality. Okay? So that is a little bit closing the loop between the three aspects. Okay, so let me begin with the global optimality part. I already did this here. Okay. So, global optimality part. So what I'm going to be showing is two big theorems. I shouldn't say big. I should say two meta theorems because I'm going to state them here in a very hand-wavy way. The first one is that if you have networks that have many parallel subnetworks, as illustrated in this picture, and you're able to find a minimum such that all of the weights of one parallel subnetwork are 0, then that is a certificate to guarantee that that's a global minimum. Okay? That's going to be the first meta theorem. The second one is that if you optimize over networks where you vary the architecture in a way that and the variation is actually very simple. The variation is add one more parallel subnetwork. Of course, that doesn't cover all the cases we're interested in, so that's what makes the results limited. Then you can guarantee that spurious local minima do not exist. So in particular, when you look at this picture, notice that this thing is not here on the right. So the actual landscape for networks that are large enough is that you can have many global minimizers, but local minima, and you can have saddle points, but local minima that are not global do not exist. The last theorem is that dropout induces low-rank regularization. So, for example, in networks with a single hidden layer, what dropout is doing is penalizing the number of neurons in that layer. Okay. So those are the three meta-theorems. So how am I going to show that? I'll begin by stating what are the assumptions on the architecture. I'll continue by stating what are the kinds of regularizers that are needed for this to be true. And then I'll probably run out of time, so I won't be able to actually go into the math of what the theorems are. But I'm happy to discuss them over lunch once we have enjoyed the game. Okay, so properties that are needed over the architecture. We will need this property called positive homogeneity. What does positive homogeneity mean? It means the following. Suppose that you've got that network that is there. Suppose that you scale the weights of the network by a scalar alpha that is non-negative. Okay? If you scale the weights, what happens to the output? So we're going to assume that the output is also scaled by that alpha, except that it's raised to some power, p. Okay? And that's what's written here in the equation. This is the standard input-output map of the network. If the weights are scaled by alpha, I get alpha to the p. All right. That property actually typically is known as homogeneity. If anyone has ever studied math, it's homogeneous functions. That's what it is. Except that I'm requiring this only for non-negative scalars. So that's why I call it positive homogeneity. By the way, this is all the work of Ben Haefele, who was a PhD student in BME. So BME students can do a lot of good math. Okay, so you may ask me, well, is this an unreasonable assumption? Or is this satisfied in practice by the networks we actually use every day? Well, let's go through the simplest single neuron. Well, scale the weights by alpha. This is just a sum, so this is linear, right, weighted sum. So sure, the output will be scaled by alpha. Now I'm going to pass this through a ReLU in here. So the input of the ReLU is scaled by alpha. Okay? And now you need to take the maximum between that and 0. Well, if alpha is non-negative, then it doesn't change which one of the two takes the maximum, right? And therefore you can take the alpha outside. You see that? That's a very important property. Okay? So again, I repeat, if you have the alpha inside, whether alpha z or 0 is bigger. When alpha is non-negative, it doesn't change which one of the two takes the maximum, so you can take it outside. So it really acts as if it was linear, that you can take the alpha. Okay, so a linear plus a ReLU is homogeneous of degree 1. What about slightly more complex networks? So suppose that I've got the input, I scale the first weight layer by alpha, and it is a convolutional plus ReLU. By convolutional is a linear, right? So linear plus ReLU. So the alpha comes out. Second layer is convolutional plus ReLU, so I scale these weights by alpha, but the input was already scaled by alpha. So now I get alpha squared after the second layer. Now I'm going to do this operation called max pooling. That's the nonlinearity now. So this means that this is scaled by alpha squared, this is scaled by alpha squared. Which one of the two takes the maximum is not affected. So I can take the alpha squared outside. So the alpha squared passes the max pooling as well. Well, the last layer is linear, so if I multiply that by alpha, and that was alpha squared, then I'm going to get alpha cubed on the other side. And then conclusion. I've got 3 weight layers, and this was alpha cubed. So typically, each weight layer will increase the degree by 1. Okay? So this is true of many other things. So it's true of convolutional, max pooling, linear layers, link pooling, many possibilities. But it's not true for sigmoids. So that's our first conjecture. I began my talk by saying, this ReLU versus sigmoid and the vanishing gradient, and then I said I'm unsatisfied by that. So this is a first conjecture that one reason why ReLU might be better than sigmoid is that at least for ReLUs we can have theorems with global optimality. For sigmoids we can't so far. Okay, so that was the first property of the architecture. It needs to be positively homogeneous, and my answer is that most networks we use are potentially positively homogeneous. The second one is this parallel subnetwork architecture. So what that means is the following. Take what I will call a subnetwork, and in this particular case is the simplest example. It's a single neuron, 3 inputs, 2 outputs. Put many copies in parallel and add them up. So that's what I will call a network that is composed of parallel subnetworks. Okay? So this is one example, and this gives rise to a network with a single hidden layer. Okay? So our results will apply to this, for example. But beyond that, you can now pick any parallel subnetwork, like this one, and just put many of them in parallel and add them up. Okay? And you could get fancier. You could AlexNet, many of them in parallel, and add them up. Okay? So bottom line is that the classes of networks we're going to have, and whenever I speak about size, the size is going to be how many parallel subnetworks I put on top. So this is a little bit less realistic in practice, because today, if you talk to practitioners, they're not using gigantic networks with many of them in parallel in this particular way. And this is an opportunity for improving the theory that I'll present today, so that it applies not only to these sort of wide networks that are being built in this way, but also, I'll explain that again, but I hope you get the message. Okay, so those are the two assumptions on the architecture. It needs to be homogeneous, and it needs to be parallel. What about the regularized? So this is the classical way of doing regularization. You always do sum of the square of the weights. Okay? All right, good. So if you think about it, what is the degree of that regularizer? It's degree 2. It's also homogeneous, and it's homogeneous of degree 2. Is that clear? Right? It's every w squared, so if you scale w by alpha, you will have alpha squared. Now, if you think about this network, it has 3 weight layers, and I convinced you earlier that typically it should be homogeneous of degree 3 because it has 3 weight layers. Right? Good. And I want to point out as well that 3 is different from 2. Okay. And I want to point out that 3 is different from 2 is exactly the source of all of the local minima. I don't have the time to explain, and a lot of it is in Ben's thesis, but the fact that you have degrees of homogeneity for the network and for the regularizer that do not match is one of the sources that causes the existence of local minima. So this is in fact, people in the past say, oh, we've used weight decay and it doesn't work, so that's why we went into dropout and we went into all of these other things. So the message that I'm trying to convey here is that if you have a network with 3 weight layers, you should have been using degree 3. If you had a network with 100 layers, you should have been using degree 100. Okay. So now you're going to ask me, how do I design something with degree 100? So the obvious answers might be that you just put the degree there, all right? But I'll show you that you can do a little bit better in the next 2 or 3 slides. So how is exactly? So how do we design a regularizer that is positively homogeneous or the same degree as the network? So here's one simple way to do it. So suppose that, again, there are many parallel subnetworks. So let me take one branch only. In this particular case now, it is 5 weight layers. Okay? So define some regularizer for those 5 weight layers. I'll tell you in a second one concrete example of how we can do it. We are going to require that regularizer to be of the same degree as that of the network. I already told you why we want that. And it needs to be positive definite. So again, think about like a square without that. But here is actually an example. You take the norm of all of the weights. So again, maybe the indices, right? This is subnetwork 1, and this is layer 1, 2, 3, 4, 5. So I'm taking for one subnetwork is all of the norm of all of the weights from layer 1, norm of all of the weights from layer 2, and so on and so forth. And I'm taking the product. By construction, that thing is degree 5. Right? And remember at the beginning of the talk, I was talking about this product of weights? That's exactly what I was talking about. Okay, that you take norms of the weights from one layer, and then you take products across. And then, so that's for one of the parallel subnetworks. You do that, and then we are going to sum in order to produce the total. So the total regularizer is sum from 1 to the number of subnetworks of the regularizer for the ith weight, the ith subnetwork. That's what it says. And so what we're going to do is that we allow this R to vary. So we're going to be optimizing over networks of variable size. And the idea is that this needs to penalize complexity and needs to penalize size. So networks with bigger size should be less preferred by the regularizer than networks of smaller size. So every time you add one extra parallel subnetwork, this regularizer is supposed to increase. Okay? So let me see how much time I have left, because I did manage to at least, I did get 9 minutes to go to some equations. Okay, so far I've told you it's kind of, I've stated in a theorem there is always if A and B, then C, right? So I told you if the architecture is homogeneous and parallel, and if the regularizer is homogeneous and adjusted to the network, as I've just described, then things go well. So what is the theorem? So rather than explaining the theory in the most complex case, which is many networks and so complex, I'm going to explain it in the case of linear networks, in which case it becomes equivalent to factorizing matrices. Okay? So think about these as the weights of the first layer, and this is the weights of the second layer. Okay? So you take an input, this is the weights of the first layer, weights of the second layer, this is the output. So this is equivalent to taking the matrix of labels and factorizing it as the product of two matrices. And the number of columns here is going to be the number of neurons of that hidden layer. Okay, so how do we do matrix factorization? The same way, the neural network way, if this was a neural network, it'll be what I have on the right. Given the matrix of labels, I want to find the network weights, U and V. I have a loss, and I have the regularizer. So this is the same thing I've been talking about so far, and this would be minimizing over the network weights. Okay. But because it's a linear network, UV transpose is just another matrix. So I could just do a substitution, and instead of using UV transpose, I could just use X. And likewise, maybe there is a way of replacing this regularizer by some regularizer only on X. So now on the left-hand side, I have something that looks simpler perhaps, particularly if the loss is convex on X, and if the regularizer here is convex on X. Then this problem on the left is convex, but the problem on the right is non-convex. So there are two ways to do it in this particular case. So how do I connect the two ways of doing things? So if the regularizer on the right is the nuclear norm, how many of you know what the nuclear norm is? One person, 2, 3, 4. Okay. I've written it here, by the way. The nuclear norm is the sum of the singular values of the matrix. Okay? The sum of the singular values. And it's supposed to be a proxy for sparsity, or sorry for the rank. Namely, small nuclear norm is a proxy for small rank. Okay, now that you know what the nuclear norm is, you think you can go and compute it, run any code, right? Yeah, okay, get singular values of a matrix and add them up. Okay, so instead of doing that, let's make it very, very complicated. And there is this theorem that says that that simple quantity that everybody can compute is equivalent to the following. Take the matrix, factorize it. The factorization might not be unique, right? I can always insert a inverse maybe in the middle. And among all u's and v's whose product is equal to x, select the one that minimizes this quantity. This is sum from 1 to the number of columns, 2 norm of ui, 2 norm of vi. This is the ith column of u, ith column of v. And these quantities are equal to each other. Minimization over uv, I didn't tell you, but also minimization over the number of columns. Okay? So in other words, if you give me a matrix and you find the optimal factorization, according to this objective, the value of the objective is equal to the nuclear norm. So what that suggests is, well, voila. Let's pick that as the regularizer that I'm going to put there. And what is that regularizer? Sum of products of norms. U sub I, what is U sub I? That is all of the weights of the ith neuron from the input layer to the mid layer. What is Vi? Is the norm of the weights of the neuron I in the output layer. So it's the sum of the product. So now it's exactly that decoupling that, you know, I say sum for each subnetwork, but each subnetwork is just one neuron here. Okay. All right. So, okay, I did this for the 2 norm, and that gives the nuclear norm, but you can generalize it. Maybe it doesn't matter here, but you can make this with any norm you want, really. It doesn't need to be the 2 norm. And that will give you a norm on the left. But here's the gist. Let me just state the message up front. The gist is the following. There is a non-convex problem on the right, training of neural networks. There is a convex problem on the left. There is a way to relate a convex regularizer to this non-convex sum of products of weight. That is exactly what is at the gist of being able to have guarantees for this non-convex problem. Namely, that is strongly related to a convex one. That's the gist of it. And so let me restate, and this is the only theorem I'm going to restate in detail just to get to the conclusions. The first theorem. The first theorem was, and maybe I'm going to go back to the meta theorem that I had put at the beginning so that you remember. Where was it? Yeah, I think here. Yes, this was the meta theorem. It was, if you train a network and you find a local minimum, and all of the weights corresponding to one parallel subnetwork are 0, that's the global optimum. That was the meta theorem. How do I say that meta theorem sort of more concretely now? So it was here. So that's the statement now, much more precise. So suppose that you consider that non-convex problem. That is the training of a neural network with a single hidden layer and linear with R neurons. Assume that the loss is convex and one's differential. Then a local minimum to this non-convex problem, so the set of weights U and V, such that all of the weights for one neuron are 0. So in this particular case, one entire column of U and one entire column of V are 0, is a global minimum. Okay? So it's the same theorem, but now stated precisely for this concrete case. And what is the reason for it and why is it true? It's because of the connection with this convex problem. Namely, that if you take this local minimum UV that has one column of zeros, and you multiply U with V by UV transpose, that gives you a matrix, and that is a global minimum of this convex problem. So really in picture, what's going on is that I've got this convex problem at the bottom, this non-convex problem. The convex problem is a global lower bound for the non-convex. And the global minimum agrees. Okay. So that's why the same local minimum for the non-convex gives you the global minimum for the convex. Okay. So I'll skip the rest and the extension to neural networks and just get to the conclusions. So there are two big messages. One of them is that size matters. Namely, today we sort of design architectures trial and error, and we modify the number of neurons and the number of layers based on performance at the end of the day. So I envision a future where we're going to have a way to optimize over the network architecture. Today, I've shown, and in fact, I didn't actually have the time to emphasize it, but we are optimizing over the number of columns of that factorization. So we're optimizing over the number of neurons of that hidden layer. So that's just one number, and that's why we need this multiple parallel substructure. In the future, we should be optimizing over a number of neurons and number of layers. Okay? And therefore, we need an extension of this theory to accommodate for more than one notion of size. The second one is that regularization matters. I think it was critical to get the results that you had this positive homogeneity, that it had the same degree. And how do you do that for more complex networks is an open question. All of the results here are high level. What I mean by that is that how do I find the global optimum? It's something I didn't touch upon. So for that, you need to compute, and depending on which regularizers and which losses, that could be easy or that could be NP hard. So we are precisely working on making algorithms that are computationally tractable for some classes of regularizers. And that's it. Thank you.
We have time for a couple of questions before we adjourn. Okay, let's start with, no, but okay.